Let's see if they are the same phenomenon in the Hanno-Tower problem. Actually, in Hanno-Tower problem, the recurrence relation is not homogeneous at first. The right-hand side is 1, and we eliminate the right-hand side by subtracting. Then we get that hn minus 3hn minus 1 plus 2hn minus 2 is equal to 0. With the same denominator manipulation, we get 1 minus 3x plus 2x squared is equal to 1 minus x times 1 minus 2x. Of course, we could again use x to the minus 1's power to solve it. But now, if we think carefully, if the correspondent Cm here is m squared minus 3m plus 2, it's correspondent to the coefficients and orders of the recurrence relation. So does that mean that we might no longer need to plug in x to the minus 1's power? Instead, we find such a corresponding Cm expression directly from the recurrence relation. So according to our definition of linear homogeneous recurrence relation, we have an plus c1 times an minus 1 plus c2 times an minus 2 until ck times an minus k is equal to 0. With the same method, could we find its generating function? For example, we assume that gx is generating function. Then gx could be expressed as a0 plus a1 times x plus until an times x to the nth power, with a1 as a coefficient in the generating function. We have encountered such situation, and we usually use a series of addition to get the impression of the generating function. We could do this again here. For example, for x to the kth power, we could use the recurrence relation to get x to the kth power times ak plus c1 times ak minus 1 plus c2 times ak minus 2 until ck times a0 is equal to 0. Similarly, for x to the k plus 1's power, we could write it as this, and until x to the nth power. This way, we could add two sides separately. Let's look at the first term. Actually, it's x to the kth power times ak plus x to the k plus 1 times ak plus 1. Compared with the original generating function, it only lacks the first k minus 1 term, so the accumulative sum of the first column is equal to jx minus the sigma of ai xi, in which I is from 0 to k minus 1. What about the second column? We would discover that it is ak minus 1 times x to the kth power. Comparing with the original generating function, it multiplies one more x, so we could take c1 and x out, and then it's gx minus aix to the ith power inside the parentheses. Also, adding all the remaining terms, the result is that the right-hand side is 0. With this formula, we could get the expression of gx. Let's see, gx times 1 plus c1x plus c2x squared until ckx to the kth power would be equal to the product of all constants, and the term irrelevant with gx in the right-hand side. With this equation, actually there is a new expression for gx. If we use px to denote the right-hand side of this expression, we could analyze that actually the order of polynomial px must be less or equal to k minus 1. And in the left-hand side, gx multiplies a polynomial, so gx equal to px divided by this polynomial. Actually, the order of this polynomial is k, so gx could be denoted by px divided by 1 plus c1x plus c2x squared until ckx to the kth power. Let's look at this expression. Could we convert it into 1 minus ax times 1 minus bx form as what we did? This requires us to analyze these denominators carefully. We want to get 1 minus ax form. What should we do? In order to use this property, we need to convert x to the minus 1's power. Here, we take x to the kth power out and then use m to replace x to the minus 1's power. So m-related terms in denominator becomes cm equal to m to the kth power plus c1 times m to the k minus 1's power until plus ck minus 1 times m plus ck. We could factorize this coefficient. After factorizing, cm has several roots, which include a1, a2, until ai. And some roots might not be single roots, but instead they are multiple roots. So Cm could be denoted by m minus a1 to the k1's power times m minus a2 to the k2's power and so on times m minus ai to the ki's power, in which k1 plus k2 plus which is the total number of roots is k. With this expression, we could substitute it with the expression and the numerator remained the same. The denominator becomes 1 minus a1x to the k1's power times 1 minus a2x to the k2's power until 1 minus aix to the ki's power. Now we have the expression and we could convert it into an undetermined coefficient over 1 minus ax plus something else. So we could see that with this analysis, the general function could become the sum of multiple Taylor expansion of something over 1 minus ax. The key step is the manipulation of the denominator to use m equal to x to the minus 1's power to replace x. So we could only need to factorize Cm to get the coefficients of 1 minus a1x, 1 minus a2x, and so on. But do we need to repeat this process every time when we solve a problem to convert this polynomial? Let's look back and we discover that, and first the recurrence relation is an an plus c1 a n minus 1 plus c2 a n minus 2 until ck a n minus k. This exactly corresponds to the Cm expression. It's correspondent in its order and the power of m's. Exactly 1-to-1 correspondence. So, for example, assume this a n minus k is correspondent to constant ck, so its previous terms are similar until the first term where its degree is k. Here, c1 a n minus 1 is correspondent to c1 m k minus 1. c2 a n minus 2 is correspondent to c2 m k minus 2. So forth. So we only need to know its recurrence relation to write this Cm expression directly. This tells us that maybe we have a direct method by using the recurrence relation. So till now, we've discovered that besides the recurrence relation, the initial values, the linear homogeneous recurrence relation have another very important element. We only need to know this linear recurrence relation to write such an expression. This expression is called the characteristic polynomial. It is a 1-to-1 correspondent to its recurrence relation. So we could say that with a recurrence relation, we only need to correspond the orders and the powers and then copy the coefficients to get its characteristic polynomial, which is Cx. Let's look at an example. For example, in Fibonacci sequence, fn minus 1 minus fn minus 2 is 0. What's its characteristic polynomial? Its order is 2. So the first term fn is corresponding to x squared, fn minus 1 corresponding to x, fn minus 2 corresponding to 1. So we could write its characteristic polynomial directly. It's x squared minus x minus 1 equal to 0. What about Hanel-Tauber? It's the same. The cross relation of Hanel-Tauber is hn minus 3 hn minus 1 plus 2 hn minus 2 equal to 0. Similarly, we could think that its characteristic polynomial is x squared minus 3x plus 2 equal to 0. With such characteristic polynomial, all linear homogeneous recurrence relation could be solved easily. We could introduce it in the next time.